Hello, good afternoon, everybody. It's welcome, everyone. And my name is Guno Son, Associate Professor at the Geomatics Engineering Program in the Lasong School of Engineering, York University. This is my great pleasure to welcome you here today on behalf of the Geomatics Engineering Programs in York. We are very much delighted to have you participate in share this talk as part of the GeoTalk virtual seminar series. This is already 8th this series, and I thank you for joining us. So Geomatics Engineering Program in York University was founded 20 years ago. So we will have a 20th birthday this year, and for 20 years in the past, many geomatics undergraduate, graduate students has been educated through our programs, and who now, working as leaders in various fields of geomatics areas as engineers, scientists, entrepreneurs, and educators. So our programs also primarily contributed to the research community and industries by conducting innovative research projects. So GeoTalks is a bi-weekly seminar series organized by Geomatics Engineering Program at York, and also together with Canadian Institute of Geomatics Toronto branch. So this series will host industry leaders and entrepreneurs in geomatics, and this is a great opportunity to hear from industry leaders, and such as Teledyne CARIS, who invited today, and share their cutting-edge geospatial technology with us. So we honored to have a Buns Foster with us today, and Buns Foster is the innovation manager for Teledyne Geospatial. His primary responsibility involves developing new products and services outside of geospatial's core competencies, and with a focus on novel application of machine learning technology across the entire geospatial domain. He previously spent 5 years as a product manager for, I don't know, you heard this famous software, HIPS and SIPS, and a Teledyne CARIS flagship processing software suite. And so today he's going to talk about the talk's title, The Hydrographic Survey, Mapping the World's Ocean in the 21st Century. So Buns will share his visions and experience at Teledyne CARIS. So now, Buns, are you ready to start your talk?
Yep, I'm ready to go.
So I'm going to stop sharing my screen.
All right, and I'll pop mine up. And we should be good to go.
Yeah, looks great.
Okay. Thanks, Guno. Great introduction. So as he mentioned, I'm going to skim across what is an absolutely massive industry, and I'm going to give you about 2 years of content in about 30 minutes. So I'll try to keep it brief and just hit the highlights. I know if my colleagues with an oceanographic background saw this, they'd jump up and down about some of the things I'm skipping, but I'm just trying to give you a general sense of what this world is like. So I thought it best to start with a definition of hydrography, what it actually means. And, to sum it up, it's basically how, measuring the ocean. So measuring the physical makeup of the ocean floor, or not even just the ocean, but lakes, rivers, streams, all that kind of thing, anything underwater, because there's a lot of extra work that goes into that, which I'm going to talk about the next half hour to get that kind of data together. The primary purpose under hydrography is to serve the purpose of safety of navigation. So mariners, anyone in a boat has a map they can use to navigate those waterways safely. But there's other stuff involved here. I'll get into that more in detail as we go on. For instance, diving a little bit deeper, what it's become much more common lately, beyond safety of navigation, is there's many other applications for this. So climate modeling, climate change, that's a big one. For instance, tsunami modeling. If you want to know how a tsunami is going to behave as it's approaching a coast, you need to know what the bathymetry looks like, and in fairly high resolution as well. Not just, oh, I know it's roughly 60 meters deep. You need to have a good understanding of the makeup of that seabed to understand what the water is going to do. Fisheries management is also huge these days, understanding things that live on and above the seabed, what their habitats look like, how their habitats are responding. A lot of times, they're deep enough that we can't dive on it or send a camera down. We need large scale mapping efforts to identify, what's happening with those systems. And that ties into something called the blue economy. I just threw it in there because that's a huge buzzword as well. I'm not going to dive into that too much, but that kind of ties in. It's more about human activity and how we can responsibly manage our ocean resources. So that's how the blue economy ties in. So a big chunk of the information that feeds the blue economy is hydrography. It's also definitely worth starting out talking about how well the world's oceans have been mapped. You've probably heard phrases like, less than 10% of the world's oceans have been mapped, or we have better maps of the moon and Mars than we do of the planet Earth. That's absolutely true. And there's a foundation called GEBCO. It's a sort of a conglomeration of many international public partners that have spearheaded the effort of bringing together, this large scale map of the ocean floor. And I guess 3 years ago now, back in 2020, the GEBCO group announced a new initiative called Seabed 2030, and the goal is to have 100% of the world's oceans mapped by the year 2030. And it's actually gone fairly well so far. So the graph there on the right, back in 2018, we were at 6.7% of the world's oceans mapped, which is minuscule when you think about it. Almost overnight, so within a year, they had more than doubled that up to nearly 15%. If I had to guess why that is, it's a lot of organizations that were sitting on data they weren't using anyway, and to gain a few brownie points with such a big international organization, they handed their data sets over to GEBCO at no cost to themselves. So that was that big initial bump, I think, with the coverage we had. But we've done really well continuing that into 2020. We're up to 19%. There's a number of partners working with GEBCO now, feeding new data into this model, and we have a shot at it. If you ask me, I wouldn't necessarily say we're going to hit 100% by 2030, but we're not going to get anywhere if we don't set a target. So it's been really encouraging to see the progress they've made so far. So if you've ever used something like Google Maps, and I'm quite sure most of you have, you may say, wait a minute, I've seen bathymetry on Google Maps. If I zoom out and start spinning around the planet, I can see mountain ranges and canyons and all kinds of neat things on the ocean floor. That seems like we've mapped 100%. So what's going on here? Well, I touched on this a minute ago. And I mentioned, we have the common phrase, the moon and Mars are better mapped than the Earth. And if you look at these three pictures, you might be able to guess why. Think about mapping Mars. Is there any liquid water on the surface? No, that makes it easy to map. Moon, same deal, easy to map. The challenge with the planet Earth is it's covered in water. About 71% of the surface of the Earth is covered in water. And that actually makes it really difficult to map compared to these other planetary bodies. And the reason for that is quite simple. Water is a really efficient attenuator for electromagnetic radiation. And electromagnetic radiation is basically the most common remote sensing technique we use. The most obvious application there is photography. So photography is collecting passively any electromagnetic emissions that are coming off the surface of the Earth. So that's photography. When you take a picture, you're just collecting EM radiation and turning that into a grid, basically. So for many years, of course, we've been using photography to map not only the Earth but other planets to great success. But the problem is, you see this, there's pretty high absorption across the spectrum from water. So EM radiation does really poorly at penetrating any body of water. We have an interesting dip right around the visible spectrum, and there's all kinds of interesting consequences to that, including life on the planet I won't get into, but it's kind of neat to think about. But that's the reason we have such trouble mapping the world's oceans, is because photography doesn't work. We can penetrate, a few meters, maybe tens of meters, in a place like Bermuda where there's really clear water. But generally speaking, it's really hard to get through. We also have active EM sources like radar and LiDAR, where we actually generate our own EM waves and send those at targets. Radar sits kind of off the right-hand end of this graph, so it's up at a much higher wavelength. LiDAR generally sits right about here in the infrared, which has a little bit of penetration, but in practical terms, we're talking centimeters. And there's also another interesting type of system called bathymetric LiDAR, which actually uses a green laser instead of a red laser, and it sits right in this little saddle here, where we've kind of maximized, or I should say minimized, the absorption for our EM radiation. But I'll talk about bathymetric LiDAR a little bit later in the presentation. So where do these maps come from? And the answer is actually something called satellite altimetry. So instead of using EM radiation, we're actually using the altitude of satellites to determine what the size and shape of the Earth looks like. So how it works is quite simply, as these satellites are moving over the Earth, as they go over regions sort of maybe higher density than other regions, the orbit of the satellite will actually change a little bit. It'll move up or down in its orbit. So as it's going along, it's almost tracing out a line for the I shouldn't say the height of things below it, but really it's how high the gravity is below the satellite. So there's a pair of satellites called GRACE that have been in use for quite a long time at this point. And there's a pair because as they're going around, what they're actually doing is we're measuring their absolute positions from the ground, of course, to see what's happening, but they're also measuring in between themselves. So they have very highly accurate measurement devices built into them, and they're constantly measuring the separation between each other at a very, very, very precise level so that they can detect those deflections as they go over different objects on the surface of the Earth. And the really neat thing is, if you look up the Earth is a potato, if you search that on Google, you'll get back this image. So despite what it looks like, this isn't an exaggerated height map of the Earth. This is an exaggerated map of gravity anomalies across the surface of the Earth. So it's a little bit different. The Earth isn't exactly shaped like this, but this is a picture of what happens with gravity in different parts. So you see some really neat things like off the southern tip of India here, or really around the whole southern tip of India, it's really low. Gravity is quite low in this region, probably due to, I'm not a geologist, but I'm guessing it's due to a thinner mantle around this part. Whereas up in the North Sea, off the coast of Scandinavia, it's very dense oceanic crust. So you get a much higher gravity anomaly in that region. And the neat thing is you can see things like here's the Himalayas. So you can clearly see a significant deflection in the gravity model because of the density, the size and density of this mountain range. So we're using this gravity model over the ocean to infer what's under the water. So, and it actually does a pretty good job of telling us that, sort of the size, contents and makeup of the ocean floor. So that's where the 81% fill-in comes from when you look at Google Maps. The other 19% comes from something called comes from sonar, a specific type of sonar called multibeam, and I'll talk about that more in a second. There's different types of sonars for different purposes. I'm not going to cover all of them because there's a huge family of sonar systems that do different things for measuring the ocean floor or the water column or a whole bunch of other things. But what I'm going to focus on today, what we use in hydrography specifically, is typically a multi-beam sonar system. And this is basically a stock unit, what it looks like. They'll get mounted on a pole. This is one that's been integrated into the bottom of a boat. So there's different ways these things get deployed, but I'll talk about that more in a minute as well. So the good folks at the University of New Hampshire Center for Coastal and Ocean Mapping. They're a bit of a powerhouse in our industry. They've got a great tool online where you can actually see the sources for all these GEBCO data sets. So they actually overlaid basically what you see in Google Maps. Google is getting that from GEBCO. That's the GEBCO map they're using for Google Earth or Google Maps. But on the UNH tool, you can actually see the data sources they've used. So in the brighter areas here, and there's things like, so here's the Mariana Trench right down here in the bottom left. This is Hawaii on the right. Up here is Alaska, just the very tip of it. This is Russia. So this part of the Pacific, we can see the sort of brighter spots. These have been mapped with multi-beam sonar, and the darker purple areas, that's from satellite altimetry. Now, if you look closely, you can actually see where there's, defined ridges in the satellite altimetry. We can confirm that with the multi-beam measurements that, yes, there is actually a ridge there. So the altimetry is a pretty good model or pretty good method to actually, characterize the ocean floor. But part of the challenge is it's subject to error. So there can be local gravity fluctuations that will throw it off. And it's very low resolution. So at this scale, basically floating high up in space, it's fine. But if you zoomed in closer to this data set, the resolution of the satellite data is much, much, much lower than the sonar data. So we don't get that level of detail. And we often need that for things like climate modeling, fisheries modeling, things like that. We need that higher resolution from sonar data versus something we get from satellite. Excuse me. So multi-beam survey, how does it work? Basically, a multi-beam sonar is kind of made up of two arrays. So these are it's basically a speaker and a microphone is how this works. So this barrel-shaped one here on the front, that's the transmitter, and so it transmits a wedge of sound, and that's kind of this red outline here. It transmits pulses or wedges of sound down to the seafloor right across. It's basically 60 degrees on each side. And then this other array, it's called the receiver. So that actually does something similar, but it's at a 90-degree angle to the transmitter, and it actually splits it up into a series of discrete wedges going across this swath. So at the intersection of the transmit pulse and each receive swath, you get a little footprint. So that's your measurement sample that gives you a range and angle for the depth, and that's how you measure the seafloor. Acoustics in general, the lower frequencies travel much further in the water. So for full ocean depth, if you're surveying the Mariana Trench, you need a really low resolution system down to like 12 kilohertz is roughly the lower range. And as it gets shallower, you can kind of go up into medium frequencies. If we're talking about coastal surveys, generally those about 200 to 400 kilohertz, sometimes higher, but those really limit you to very shallow waters, like a few meters. But generally speaking, the vast majority of the mapping that takes place is in kind of this high frequency region, 200 to 400 kilohertz along coastlines, because that's where the human activity is, and that's where everybody really wants to know what the seafloor looks like. Once you get back, I kind of mentioned this already, range and angle from the intersection of these two footprints, but you can also get an intensity of the response. So depending on the characteristics of the seabed, you'll get a different intensity on the return. So for instance, sandy gravel, that'll give you a really strong reflection because there's lots of tiny edges on all the sand grains that are really good at bouncing the sound back to you. Something like sheer rock, like bedrock, is actually darker in the image because the sound wave bounces away instead of back to the boat. So that's kind of the interesting thing, but you can use that reflectance not only to measure, what the shape of the seafloor is, but also what it's made up of. You can make some good inferences about that. And for the really hardcore guys, they can actually log the full time series. So not just the time that the pulse hit the seafloor, but everything that happened in between in the water column. Fisheries guys do this, and you can actually see things like fish in the water column, or more appropriately for oil and gas, if there's hydrocarbons, generally they'll create a bubble stream coming up from the seabed, and obviously oil and gas companies want to find those bubble streams because that means that's a place they should put an oil rig. So I kind of mentioned this already. There's different ranges of sonars. Like I said, that this is the most common, kind of up here in the shallower 0 to 500 meter range. And then you get bigger systems, like I said, up down to about 12 kilohertz and full ocean depth of about 11 kilometers. The neat part is, if basically that the size of the sample you can get back from the seafloor is limited by the size of this transmit pulse, the width of it, and this receive beam. And the smallest they get generally is about 1/2 degree. So you get a 1/2 degree by 1/2 degree square intersection here on the seafloor. So that's what's fixed. So when you're talking about how dense your data can be, well, you're limited by that 1/2 degree. In full ocean depth, 11,000 meter or 11,000 meters. That's roughly 100 by 100 meters. So every point that comes back from this receive swath at full ocean depth is like 100 meters wide. So you're really limited by your resolution in that case. Of course, some smart people figured out you can take a sonar and stick it on a robot that can dive, and you can actually bring the sonar nice and close to the seafloor and map it that way. So if you need the resolution, and this typically would be cable laying vessels, so if you're trying to put a fiber optic cable or a pipeline or electrical cables or something across deep ocean seafloor, they have to get an AUV because the AUV will fly along the seafloor on the bottom and actually measure it that way up close. And that way they can get the resolution they need to plan their pipeline routes. Of course, the other thing I should mention is cost increases from left to right and from top to bottom. So when you get into deep water AUV systems, you need a big ocean going platform for that AUV, and then the AUV itself. I mean, we're talking hundreds of millions of dollars involved here just to do this kind of survey. There's other types of sonars. A very common one you might have heard about, side scan sonar. So this is a purely an imaging system. This is kind of a bad example picture. Usually they don't mount them right on the boat. They're usually towed behind a boat on a cable. And that way they can actually put the sensor very close to the seafloor. Just so the geometry gets much nicer. You can see shadows and artifacts, that kind of thing. Side scan is really common with search and rescue people. So there's a lot of search and rescue groups because you don't necessarily care about mapping the seafloor. You're trying to find something standing, sitting on top of the seafloor. So that's where these imaging systems come in. They're much cheaper than a multi-beam. Multi-beam is probably the most expensive type. Side scan is much cheaper. You can survey a lot faster. You can cover more ground, but you only get an image back. So it's just a picture of the seafloor. You can't really take any measurements from it other than the height of something, but I won't get into that. But they are very high resolution, which is nice. Single beam, of course, if you've ever been on any kind of pleasure boat, even 9 times out of 10, they have they'll call it a fish finder. Basically just a single beam is just a survey grade version of that. It just transmits a single pulse straight down below the boat and measures a response coming back. Quite cheap, quite simple. This is a poor man's survey system, but of course you don't get the coverage that you would with a full multi-beam or even a side scan for that matter. A lot of organizations, especially let's say countries that don't do as well economically, they'll actually combine a single beam and a side scan. So they'll get some seafloor depth measurements from the single beam, and then they'll have the side scan to kind of back them up to make sure they don't miss anything. So if they see something in the side scan, they can turn around, go back and run over it with the single beam to make sure they get the depth on it. And that's kind of the poor man's version of how to do survey. So what it looks like on one of these boats, this is the NOAA ship Thomas Jefferson. We were off the coast of Georgia. When was this? 2018, I think. And basically it's actually reverse order. So this was the first picture. So this was the crew deploying survey launch off the side of the boat. So the TJ has 2 boats, 1 on each side. So they deployed it off the side, they hold it there, we hop on, and then the launch goes off. And basically this boat, the smaller boat, is a survey boat on its own. So it's got a sonar and a GPS and all that stuff on it. And the ship does as well. So what these big ocean going ships do is they pull into a region, they drop their 2 boats in the water, the 2 boats go off and survey, and your big ship goes to survey too. So all 3 boats are off doing mapping exercises. So it's basically, it's a big cost saving measure where you can collect, 3 times the data in this case versus what you would have had with 1 ship alone. So this was kind of fun. This is what they call the plot room. This is Josh. Say hi, Josh. This is basically the operating center on the ship for the sonar. So as you might expect, the biggest screen is the multi-beam itself. It's not really doing anything right now, but you can kind of see the fan. So this is the fan that the operator sees. This is what's going on in real time with that transmit, pulse, and receive. And then if we're actually moving at the time and mapping, you'd see kind of you'd see the seabed here being generated in an image up here in this main display, and a few other bits and bobs. The TJ actually also tows a side scan. So they do multi-beam and side scan at the same time. I won't get into the reasons why. So they actually have a side scan being towed behind the ship. That makes maneuvers really complicated. Think about, trying to drive a truck with a trailer attached to it. It's harder to back up, for instance. Same deal with towing a side scan. So they've got cameras here to keep an eye on it, to make sure the cable's in the right place. It's not getting snagged on something. They're not going to run over it, that kind of thing. But that's generally what life at sea looks like for these deep water vessels. Lots of other types of platforms out there these days. Unmanned especially is really taking off. You get things like these small nearshore boats. Basically one guy can pull up to the beach in a pickup truck, drop this off the back and start driving it around. They're semi-autonomous. They have some autonomy built into them, but that's still a work in progress. But they could do nearshore quick day jobs with these systems. This was a fun one. We participated in the Shell X Prize. So there's an X Prize related to ocean mapping. You can Google that, it'll come right up. So we were part of the winning team. This one was really cool because this is an unmanned surface vessel. So this thing is completely autonomous and it drives around and identifies locations it's got to go map. And it actually has one of these subsurface AUVs on board. So it's a robot deploying a subsea robot, and they both go off and do their own mapping. And then the subsea robot comes back and docks with the surface robot again. Really, really cool stuff. And we did a proof of concept there. I think geez, COVID's messed up my time slot, but I think it might have been 2 years ago now, but this was totally successful. And that was a lot of fun. Sail Drone is another really exciting company. They've got fleets of autonomous craft out on the ocean now, doing various, not just mapping, but general oceanographic work, where they're doing things like measuring ocean currents, ocean hurricanes, all kinds of fun stuff. I've got a better picture here in a sec. These guys, of course, are the subsurface. So talking more about the sail drone, this is a close-up. You don't see it, but under the water line is this big gondola. And the reason for that is when depending on the hull design, as it's steaming along, you can get a lot of bubbles coming down the hull. And when the bubbles go across the transducer face, it really messes up the sound wave because you're going from water to air to water. And so especially on these smaller boats, what they'll try and do is put them on what's called a gondola that hangs below the vessel that pushes the sensors down below that bubble stream so they don't get messed up when they're collecting data. This one's crazy that they just launched this a few weeks ago. This big array, these two big arrays here, that's a deep water multi-beam system. So that's basically your full ocean depth sonar. And they actually have a second shallow water multi-beam over here on the side. So they got two different sort of ranges built right into the system. There's a couple other sonars built into this. That's what all these pucks are for. I'm not going to get into those because we're talking about mapping today, but it's a really cool system. Totally recommend you go check it out. And this thing is huge. Like that's a boat with people in it. Right here on the side. So this thing is absolutely massive. So some challenges involved. Sound speed is a big issue. So we have to drop probes to actually measure the contents of the water column. And you get, basically this is measuring the speed of sound as you go deeper in the water. And what happens is during the day, the surface warms up. So that's where this big bend comes in, and that can really mess up your sonar system. So you got to measure it constantly to keep up on top of it. Unfortunately, for the smaller systems, you have to stop the boat to deploy this thing down and measure it, and then you can keep going. Some bigger systems have what's called a moving vessel profiler that does this automatically for you. This is a really cool example of going from a river to the ocean and back. So this red spot is actually fresh water as the vessel is steaming out of the river, and then they get into the ocean, and then they're going back up the river again. And you get some really crazy sound artifacts when you do this, and you get data that looks like this. So this is sort of a 2D profile of what that looks like. So here's sort of a vertical slice across the seabed, and the edges get pulled up. When you haven't measured your sound speed correctly, you'll get a smile or you get a frown. The edges get pushed up or down. And this is something that is extremely labor intensive to correct. You have to do it by hand, and you have to step through the data to try and figure out what the proper speed should have been. Tides are a whole other thing. I won't get into that too much, but I'll just say that there are people that make their entire career out of just measuring tides. So it is that complicated. There are scientists, pretty much any government agency dedicated just to measuring tides because it is so complicated. Things like tidal modeling. So depending on the topography of the seafloor, topography of the land, how water gets funneled in around islands, things like that. Measuring tides is a huge endeavor, and you need to know the tide in the region you're measuring to know what the lowest depth is going to be, because that's what the mariners are concerned about. I see I'm coming up on the end of my time, so I'll try and steam through this quick. Vessel offsets. So we've got dual GPS antennas to give us heading, motion sensor to give us instantaneous motion, and of course the sonar. We've got to reference all that together. That can go horribly wrong. And how to make a map. So we take the sensor data, we model it, create contours and spot heights, and turn that into products, ship that out through end users. Of course, CARIS, this is our bread and butter. We're kind of the Microsoft of this world. So we're everywhere. Any big government, we're at 95% of the government agencies globally for doing ocean mapping. So our entire software stack, we've taken the raw sensor data, process it, do some analysis on it, and then generate cartographic products from it. So I'm going to just steam through this quick. So like I said, we take the sonar range, the heading, pitch, and roll from the IMU, your position and height from the GPS, turn it into a point cloud. And then we take the point cloud and we turn that into a digital terrain model. So we basically create a grid and we sample at each point in the grid, we sample a depth, the average depth in that spot, and we turn that into what we call a DTM. From the DTM, we make contour lines, and then we decimate the DTM and decimate it again until we get these spot heights that they put on the nautical chart. So this is how you get, and this only in the last 12 months have we actually managed to automate this entire workflow, because this was a very laborious, person-intensive process before this. So we've managed to build some really smart tools into our software that let you do this automatically. And then they turn that into a paper chart, which is on the left, or an electronic chart. This is becoming more and more common on the right, the electronic version of the paper, where you can actually zoom in and out different scales and actually query things. Like if I see a buoy, I want to click on that buoy and see what kind of light it has on it, things like that. So this is getting high tech. So I just want to switch gears here towards the end. I'll try and wrap this up quick. So that's the industry in a nutshell. So I want to take a minute now just to talk about the trends and what's coming, or at least what I see is coming down the pipeline. So on the industry side, the sensors are getting better. Everybody's collecting more data. And so that's turning into a huge bottleneck where we have this huge volume of data. And we're talking petabytes coming in from these various ocean going platforms or nearshore platforms, whatever, into these big government agencies that are trying to map the ocean floor. So these government agencies have these massive warehouses. And again, this is petabyte scale, if not zettabyte scale, where they've got to manage these massive data sets and turn around and provide them to their end users, whether that's, the public, other government agencies, someone trying to do climate modeling, whatever the case may be. It's a huge task. And on the flip side, mariners are a very stubborn group. They really do not like to change, but it is inevitable. There have already been several trials, for instance, of autonomous ships. So big tanker ships that can drive around the ocean themselves. And the nautical chart isn't really well suited to teaching a computer how to navigate. It's much better to give it, say the raw grid that came out of this multi-beam system, and it can use that to navigate instead. So the types of data they need to serve up has been changing quite a bit as well. Also, these deep water systems, they're hugely expensive to operate. We're talking tens, if not hundreds of $1,000s per day to operate these systems. So what people have been trying to do is maximize the time on the ship and adding more sensors to the boat as it goes out. So not just bathymetry, but also say seismic sub-bottom stuff, fisheries applications, backscatter, fish stocks. These deep water vessels are getting more and more tasks put on them, and that just means, again, more and more data coming back. And then the end users are changing as well. It's quite interesting. I'm a millennial. I've grown up around Google Maps, and people younger than myself has, so they have different expectations. If you give them a paper chart, someone who's under 40 years old, they're going to say, what is this thing? Give me a Google Maps interface and I know how to use that. So the expectations on the user side is changing quite a bit as well. And fundamental to that is standards as well. So we're members of the International Hydrographic Organizations. They dictate what goes on a chart. So what a chart looks like, whether you're in Halifax or you're in Sydney, Australia, there's one set of standards that everybody has to follow. That's dictated by the IHO. So we're an advisory to that group. OGC, the Open Geospatial Consortium, they deal with internet data standards and how data gets exchanged between different software on the web. We're part of that group as well, and we help drive those standards to make sure that everybody has access to that data. That's a big part of it as well. Okay, so big trends in the industry. AI, of course, everybody's talked about this. We've got chatbots, we've got routing, we've got fraud protection, we've got spam. It's a big thing I've been focused on in my work. Right now, mostly cleaning out noise. Noise is still a big manual time sink that people have to spend time doing or removing noise. So we have a sonar noise classifier, a LiDAR noise classifier, and a bathymetric LiDAR noise classifier as well to clean out that noise. We also are using it to identify for a bathymetric LiDAR system whether that green laser pulse just hit the land or traveled through the air, went through the water and came back, because the refraction corrections, so accounting for how the light deflected as it traveled through that, you need to know that up front before you can process it. So that was a big thing that we've automated now with AI. Cloud technologies, our cloud platform is, our AI platform is entirely deployed on the cloud, on AWS specifically. That's changing things. You know, as long as you have a credit card, you can access any number of computers that you need to perform a particular task. So the scalability available to us now is massive, absolutely massive, more than it used to be. This one I want to highlight specifically because I can't overstate how much this is going to change the marine industry with Starlink, especially coming online, you know, end of this year or next. Right now, you go a few kilometers offshore, you have no internet. There's no cell coverage. There's satellite, but these are geostationary orbits. They're super far out, so they're super slow and they're really low bandwidth. We're talking like 5 megabits. I mean, they're nothing. You can't push any kind of research information over that limited bandwidth. Starlink is 200 and low latency. It's going to change the game offshore in the next couple of years. It's going to be absolutely massive once they get that working, because all of a sudden we're going to have that connectivity in the middle of the ocean, and that's a game changer for getting that massive amount of data off the vessel quicker. Batteries, long endurance vehicles. This is a sail drone swarm. So I talked about sail drone earlier, and that massive one they built. Their bread and butter are these smaller craft that have the same design. These guys are out, you know, in the Antarctic, in the Arctic, in the Pacific right now, doing ocean measurements. Really cool. They're long endurance vehicles with the batteries. Same thing with subsurface. So where we're going with all this is manned and unmanned craft out in the middle of the ocean, pushing live data streams, high density data streams by satellite into a cloud system where it's accessible to anybody, particularly, you know, operators that can work from home, monitor this thing from the beach, make sure the data quality is good coming in, and then push these out as products to their end users who are, since it's already on the cloud, it's also democratized. So this is where we're going. Okay, I had to speed up there at the end. More content than I thought. Any questions?
Thanks, Buns. It's quite a bit of emerging technology. I love a lot. Thank you so much, Buns. Right. Okay, so I guess you know, a lot of people have questions for Buns, and if you have any, and please leave your question in a chat box so that I can deliver your question to Buns. Okay. So while people is writing the questions, I have a few questions, Buns, right? So, and in my knowledge, Buns, and you know, understanding the radiative interactions between whatever passive and active power source and water, the columns, right? And it's very difficult. And so therefore, whatever you're measuring from the water, and so you have to go through it, and we call the normalize, and by understanding the clarity of waters and
Yeah.
constant water, right? So, but that information is really hard to estimate in advance, right? And so, how could you say? And you're talking about a lot of emerging techniques, but still the scientific fundamental science. I don't know how much the accuracy-wise, and for addressing improving the accuracy based on the measurements done with LiDAR, bathymetric LiDAR or sonar, right?
Yeah.
So,
Let me see. Oh, I don't know if I left that in. I did. So I have a little Easter egg here related to that. So this is from a company called TCARTA. It's called satellite derived bathymetry. And we've been talking to them for a while about and there's ways to get their data products into our software. But yeah, it's basically they have a reflectance model effectively that they feed in, and they can actually take satellite imagery and apply some geomatics based techniques, let's call it, some physical techniques to derive it, to derive seabed just from that passively sensed data. It's moderately noisy. It's highly dependent, of course, on the clarity of the water. This is one of the Pacific atolls, basically. So it's very clear water. There's not many organisms in it. So you can get down to, let's say, 10, 15 meters of water depth. So techniques like that, it's good for near shore information. So data that's very shallow. So depending on the application, of course, the interesting thing is, the vast majority of human activity is in water shallower than, let's say, 20 meters. Once you get deeper than that, I mean, the biggest post-Panamax vessels are drafting, well, okay, let's say down to 40 meters now. But even beyond that, the only application for that deeper data is really, something like climate modeling or fisheries. If you're worried about getting your shipping container in, sometimes a data set like this would be good enough. And in fact, that's one of the that's one of the applications they actually tout for this, is actually sort of a pre-survey investigation into generally what the bathymetry looks like, or what the seabed looks like, before you send a real ship into survey. So you understand where there might be some danger. You can't make a chart from it. It's not quite accurate enough, and it's a little bit too noisy, but it's good enough for reconnaissance. So you can say, okay, I generally understand what the seafloor is doing in this area.
I see. But still, we relies on the mathematical model for normalizing it, or
Yeah.
in a way that like data centric, like using the AI for normalizing it.
Yeah, and it's well, I don't want to say too much, but there's been discussions around that.
I see. So I start to receive some questions. First, the questions from Colin. And how do you see crowdsourced bathymetric impacting?
Excellent question, because we've been in the center of this for better or for worse for a number of years. Only as like I said, we're the Microsoft of this industry, so we get pulled into these conversations. First, I want to clarify that we talk about crowdsourcing things, crowdsourcing work, crowdsourcing data. There are different government organizations that are actually in charge of mapping have a different definition of what crowdsource means. So I want to state that up front. So I won't name names, but for certain organizations, government organizations, they interpret crowdsource to mean is data collected by other government organizations, not by the public, but by other government organizations. So let's say the mapping agency, they have a sister agency that does scientific mapping. So they don't really care. The scientific group doesn't care about having the data accurate. They just need to know generally, okay, this is a reef, that's a seagrass area, that kind of thing. They don't really care about accuracy. So the mapping agencies consider that low quality data, but they will take it as crowdsourced. So that's different from Joe Blow with a fish finder and a GPS on his boat, collecting data around his favorite fishing spot. That's a different, much lower level. But there's different groups, and there's actually companies you can buy kit today to do that, where you put this little box on your boat and hook it up to your fish finder and your GPS, and you just map everywhere you go, and it pushes the data up periodically through cell service to this company. And you actually, the benefit you get back from from paying for this service is you get access to everybody else's data too. So over time, assuming you had 1,000 fishing boats in the same spot, in theory, the true seafloor is going to average out eventually. That's the theory. That's going to be interesting. We'll see where that goes. The mapping agencies really don't like that stuff. They have no interest in it. It's just too low quality for them. They're they need top shelf data only. But we'll see. We'll see where it goes. Like you said, or like I said, if you get 1,000 or 1,000,000 boats over time and they all give, plus or minus this amount, well, you can say, okay, well, actually that's not bad. I can use this.
I see. Before I reading the second questions, we on the land side, right? There's a lot of self-autonomous driving has been introduced. We expecting to see actual the robots and taxi robots and delivery bots on the street. And therefore, it's a lot of interesting the demands for getting the high definition mapping, the routing, geospatial engineering too.
Mm-hmm.
So do you also see in future like autonomous transportation in ocean side as well?
That's it. As I mentioned on this slide, it's already happened. They've already done prototypes. Yeah, and similar to navigating on land, like the Tesla systems, for instance, going down the freeway at 100 miles an hour, that autopilot's perfect for that. The problems start when you get into city traffic. So it's exactly the same thing offshore. Transiting the Pacific or transiting the Atlantic, it's no problem to make that autonomous. It already is autonomous. There's already autopilot systems that do that. But when you get into port, that's when the trouble starts, because you've got other ships that you can't necessarily predict what they're going to do. There's hazard warnings and signals and all these kinds of things that the human operator needs to account for and adjust the course accordingly. So it's the exact same problem that on land autonomous driving has. So I think as quickly as the land side evolves, I expect the marine side to evolve as well.
Okay. Right. So now I'm reading another questions from Arash. Thanks for your awesome presentation. I work in wireline logging company where we use tools pushing into oil borehole and got some logs from in a range of a meter down the ground. Is the multi-beam sonar is doing the same thing?
Yeah. Let me back up. Or no, sorry, go forward a little bit. So you're probably talking about something like this image. So this is actually a seismic image. So this is actually the top of the dark line here. That's actually the seabed. And if we go to lower frequencies, the lower you go, the more it penetrates the ground. With mapping systems, we obviously want to stop at the top of the seabed so we know where that is. But if you're doing, say, oil and gas, yeah, you want to actually go down below that. So it's very similar technology. In fact, I'd say it's almost identical. The difference is just in the frequency you're operating at. So yes.
Okay, right. So I'm waiting for the questions from the audience, and feel free to write your questions here. And Buns, when you say the seabed mapping is could you explain a little bit more? And the mapping means more for purpose for charting. Maybe what about this, habitat mapping? What about the detecting some objects on oceans? Right?
Yep. Yeah. Mapping is the most, let's call it, demanding, I think, for safety and navigation, and making, maps, charting, where things are so that ships can avoid them. But that what falls out of that, of course, is other interest groups. So one of the big products they look for is it's hard to tell here. This is actually a reflectance map I talked about kind of at the start. So instead of we have the bathymetry, we have the depth in this region, but we also have the reflection. Or a measurement of the reflection coming back from the seabed. And with this kind of map, you can pick out, seagrass, bedrock, sand, gravel, different types of sediment. And of course, scientists use that to determine where the likely, fish habitats are, particularly from, the bottom dwelling ones, the ones that live on the bottom. But even to an extent, if you've got, mid-water species that dive down to feed on the bottom, you can also predict things like that where they're going. And then I know like NOAA Fisheries is a good example. They actually use a version of this. So this fan is actually a screen grab of the real time, what you get in the water column. This is actually a gas seep coming up here in the middle. So this is actually hydrocarbons leaking off the seabed, making a bubble stream up in the water column. So of course, oil and gas is interested in that. But with fisheries, they have a similar system. It's not recording the depth. They're just looking for fish. So they'll see if you see a big school of fish, a big bait ball, or whales, whatever, they'll actually show up in the sonar, and you'll be able to actually, draw a box around the screen and measure the diameter of the bait ball, so you can estimate how many species are in there. So you can use that for the same kind of applications.
So you said the 81% of oceans are not mapped.
Not with sonar.
Right. Okay. So is it mainly because of limitation of technology, or mainly because the cost is huge? It's expensive?
It's yeah. Cost is a big factor, and desire. I'll suggest that areas of the seabed where there's a lot of, let's say, economic interest. So things like oil and gas or minerals, things like that, those have all been very well mapped because there's incentives, there's money in it to map those regions. And interesting, actually, I should mention, I'm sure you're all familiar with the search for the MH370. And I showed you, where was that graph? I go all the way back. So they searched with multi-beam sonar and with AUVs. They searched an absolutely massive portion of the Pacific. Where was that? Oh, no, I think we're all the way back at the start. Yeah, so a big chunk of this jump from 2018 to 2020, a big chunk of that was just the MH370 data, because all of that data was given to JEBCO.
I see.
So, and they mapped an absolutely massive massive chunk of seafloor. I was at a conference where the company that did the survey actually did a printout of the survey, like a printout of the DTM that they generated. I came in a roll, and they stood on the end of the stage and threw the roll off, and it went for a good 20-25 feet away from the edge of the stage. That's how big the area was.
I see. Okay, let's talk about an AI. So, it seems like CARIS is so far successful for applying an AI for denoising.
Yeah.
To receive the data, right? So, other than that, denoising, so what is your plan? What do you think, which areas you see great potential to solve the problems with a data-centric approach?
There's a couple of different areas. We started with that one first. I kind of mentioned it on that slide. When we talk to our users, unfortunately, we have a lot of great ones that like to talk to us. That we quickly discovered that was one of the most laborious things they had to do was spend hours and hours going through these data sets trying to remove the noise, because you can't move on, you can't make products until you get rid of that noise. So that's why we tackled the denoising first. And interestingly, I've heard, it leads into the AI as well. If we want to start doing things like object detection, finding things on the seafloor automatically using AI, the noise was going to interfere with that anyway. So the logical first step was tackling that noise problem. So now that we've tackled that, and actually does really, really well. So then we can kind of get into some automated steps where, okay, first automatic step is remove the noise. Second automated step is find the things I want to find. So that could be objects sticking off the seafloor. We just analyze the point cloud to do that. It could be find me certain habitats. So then we can combine position and reflectance, for instance, to try and find certain habitat areas we want to find. So that's going to be the next step offshore. I know it's been quite interesting on the land side. Everybody's interested in AI that will segment, say, a building from a tree, from a road, from a lamppost. None of that exists underwater. It's actually, it's a lot of just flat, boring terrain. Now, there's some interesting things down there, but it's not nearly as dynamic as you experience on land. So the approach has to be a little bit different for the marine world than it is on the terrestrial side. So,
Right.
So that's the kind of thing we're looking forward to.
Right. So I think in relation to that question, I have one question from Costa Cosmetics, one of my colleagues at York. Thanks, Buns, for the very informative presentation. While you touched about noise, could you please comment on how we can assign reliability and confidence in the depth determination for the blind type of bathymetric survey? That is one of two questions.
Yeah, so I didn't touch on that at all, but uncertainty measurement or the quantification of uncertainty is absolutely massive in this mapping industry. That the unique problem with mapping in the ocean is you can't see what you're measuring.
Yeah.
So you have to hope for the best that the measurements you're making are accurate. Well, there's a fairly intensive uncertainty model used across the industry to actually quantify how accurate we expect our measurements to be. They're very good at modeling random noise. Of course, systematic noise is a whole other endeavor, and there's various techniques employed to do that. We can actually use like a single pass of the sonar across the seafloor to estimate if we have any systematic errors with our vessel. So I briefly popped up, we've got the GPS antenna, the motion sensor, and the sonar, and you have to have a very precise measurement of the distance between those three things in order to correctly orient the data. We can take a short strip of the seafloor as the sonar passed across it, and we can use that to estimate how good that measurement was between the sensors. Because if the measurement is off, it's going to produce specific patterns of offsets in the data. We're going to see weird wobbles and things like that appear in the data set. So we can actually use the measured data to estimate how accurate our vessel measurements were. Then the other big aspect is dealing with, removing a tidal effect, for instance. You hope you've measured the right time for the tide you're removing, but that isn't always the case. So usually what happens is a survey will kind of go back and forth over the seabed over the course of the day. And at the end of the day, they'll drive straight across the region they just did. So if there's any temporal effects that you wouldn't have caught as you're going back and forth, by passing over it at the end of the day, called a cross-check line, that'll make any long-term temporal effects very apparent in the data set. So that's just some examples of how we deal with that.
Right. Well, there are other questions from the Costas, and he want to clarify some your talk, and could you please clarify the satellite altimetry? And he thought this is about the sea surface topography rather than the depth measurement.
Yep, that's absolutely. So there's there are satellite systems that and maybe I'm using the wrong phrase for satellite altimetry, but the GRACE satellite specifically is about measuring gravity. So it's well, it is satellite-based altimetry. We are looking at the altitude of the satellites as they move up and down. But talking about sea surface topography, that's the satellite looking down, measuring the distance to the surface of the ocean. So it's using radar to actually bounce wave off and get a measurement back to see how high the sea surface is. On the flip side, with these satellites, we're watching the position of the satellite. And we're watching it move up and down because that informs us about what gravity is doing at a specific region, if that makes sense. So it's still, they're both, satellite altimeter, we're both measuring the altitude, if you will. It's just for different reasons.
I see. Okay.
If that clarifies it.
Right. I think he said thank you. So another the questions, I think we have almost used up the time. Okay, well, let's go with these questions, Buns. And from Arash, sonar system by your account are working on reflection of sounds, and while we have some static structure in seabed, I think we talk about this. How this system distinguishes from dynamic object like fishes? Is this dynamic object causing noise either? Yes, of course. I think
Yep, it absolutely is an issue. Let me just get to my AI slide. Yep, here's a good example. So I had this point cloud shown earlier, all nice and cleaned up. This is what the original actually looked at. So you can see all these gray dots, both above and below the seabed. This is noise. So we deal with things like you said, fish. Will show up as a detection. We have random. The ocean is a very acoustically noisy environment. There's lots of stuff in the ocean making noise, so there's always going to be some level of interference with the sensor, ignoring just its background noise. Anyway, we get things like it's kind of hard. You kind of see this linear pattern here above the shipwreck. So what's actually happening there is that bubble sweep I talked about. So the hull of the boat is of a certain design where it's prone to getting wash and bubbles sweeping down the bottom of the hull. And when those bubbles pass over the face of the sonar, it kind of blips. It kind of blips on the sonar. So that's what this line, there's 3 lines above the data set. They're actually tracing out the path of the sonar in the water column. So you can actually see physically where the boat was relative to the sea floor. So there's all kinds of these effects, and this is exactly why we developed an AI platform to try and remove those systems.
Okay, so before the closing sessions, could you, I know you graduated from geomatics in New Brunswick, am I right?
Yep, University of New Brunswick, geomatics engineering, yes.
Okay, and also the CARIS is actually studied from that department.
The same faculty, yes.
So could you share us like, you know, the geomatics and how you ended up with this oceanographies and promoting like, you know, to say something about the geomatics?
Yeah, funny enough, I'll try to be very brief. So it is a short story. I was always interested in mapping. My father was involved in mapping when I was growing up. So I kind of got into that, primarily in land survey though, and mapping on land. When I graduated from UNB here in Fredericton, my wife indicated she wanted to stay in town with some family. She had some family in town. She didn't want to move. And one of the only options for work around here in mapping is with CARIS, who deals with ocean mapping. So I kind of fell into it that way. Not to say I didn't have an interest in it. I certainly did. But I kind of fell into it by accident. And it's been quite the educational experience ever since.
Okay. So do you think there's a lot of things that geospatial people can do and contribute to ocean mapping?
Oh, absolutely. I mean, we're at the wheel. We're driving it. So.
Okay. Thank you so much, Buns. So I think this is the end of the sessions. I'm sincerely thank Buns for sharing your exciting knowledge and interesting experience with CARIS, right? We very much enjoying your presentation. Thanks for your time, and also the thanks for the audience. So 2 weeks after, we invite another excellent colleagues at Teledyne Optic, and Andrew Zitt is going to talking about latest developments on the airborne laser scanner at Teledyne Optic. So please, I hope that I can see many of you 2 weeks after. Thanks, Buns.
My pleasure.
Okay, thanks everybody. See you later. Bye.